Faraday's law. We saw earlier how relative motion between a magnet and a solenoid induces a current in the solenoid. Let us investigate what changes when there is a relative motion between the magnet and the solenoid. There is a magnetic flux associated with the solenoid when the magnet is in the vicinity of the solenoid. Phi equals BA cos theta. B represents the magnetic field of the magnet. A is the cross-sectional area of the solenoid, and theta is 0 degrees in this case. As the north pole of the bar magnet is moved into the solenoid, the number of field lines of the magnet interacting with the solenoid increases. This increases the magnetic field and hence the magnetic flux associated with the solenoid. According to Faraday's law, this change in magnetic flux causes an induced EMF in the solenoid that opposes the change in flux. Faraday's law of electromagnetic induction states that the induced EMF produced in a loop is proportional to the rate of change of magnetic flux through the loop. The induced EMF is responsible for a current to flow in the loop where the flux changes. This was observed by Michael Faraday in his experiments. Mathematically, the law can be expressed by the equation EMF epsilon equals -n times delta phi over delta t, where phi is the magnetic flux through one loop of wire, n is the number of loops, and delta phi over delta t gives the rate of change of magnetic flux with respect to time. The minus sign in the equation indicates that the induced EMF opposes the change in magnetic flux. Recall that the magnetic flux is given by phi equals BA cos theta, and it therefore changes when either the magnetic field, the area of the loop, or the angle between the field and the normal to the loop changes.
Starting to feel it? Now go master it with